cross-validation and logistic regression. And if we get far enough, we'll start talking about numerical optimization. You're going to see that this all fits with what we've been doing up to now. The logistic regression is something called a generalized linear model. And much of what you learned about linear models will be true about logistic regression models, except that you don't estimate them the same way. And the theoretical properties of the estimators are different. You don't have unbiasedness. You don't necessarily have efficiency. What you have is large sample unbiasedness or consistency and approximate normality. And we'll talk some about that as we go along. So we've talked about training error versus test error. And recall the distinction between the test error and the training error. The test error is the average error that results from using a new statistical learning model to predict the response from a new observation, one that was not used in the training method. Okay? The training error is calculated by applying the statistical learning method to the observations that were used in training. So it's the out of sample. I have a question. Herbert, can you admit the people who are coming in, or do I have to do that?
Yeah, sure, I can do that.
Okay. So the training error is essentially the out of sample error, and it's the one that makes the most sense. I was talking with one of my honors students today, and he had done a study where he got an in-sample R-squared of 0.98. And we were both worried about that. I hadn't realized he was in-sample. My guess is he overfit. And so I suggested split your sample and let's see what the out-of-sample fit is, the out-of-sample R-squared. And I think I mentioned to you guys how to calculate the out-of-sample R-squared. The other point is that even when you are doing inference, you really have to split your sample. If you do any sort of model selection, you have to split your sample, okay? The training error is often quite different from the test error rate, and in particular, the former can dramatically underestimate the latter. I realize there's this little arrow here. That's because I had an FF in there, and when I converted it to a PDF and back, it turned the FF into that arrow. It's irritating. Remember the training versus test set performance, okay? We have the model complexity down here. That might be the number of variables we have. If we have something approximated by a polynomial, it might be the degree of the polynomial. When we do random forests, it's going to be how deep things are and some other issues. High bias will go with low variance and large prediction error. Low variance goes, hog variance goes with low bias, and a low in-sample prediction error, but a high out-of-sample prediction error. And what we want to do is we want to pick a model somewhere in here. Best solution is to have a large designated test set, but that's often not available. So some methods make a mathematical adjustment to the training error in order to estimate the test error rate. Some of you have seen the CP statistic, the AIC, and the BIC, and we'll talk about this later on in the course. I don't want to talk about them right now. I want to tie this into our discussion of local models. Okay. Here instead, we consider a class of methods that estimate the test error by holding out a subset of the training observations and then applying the statistical method to those held out observations. And you'll see what I mean here in a minute. So the validation set approach, which we've talked about earlier, is we randomly divide the available set into two samples, a training part and a validation, holdout, or test part. The model is fit on the training set. The fitted model is used to predict the responses in the validation set. The resulting validation set error provides an estimate of the test error. And you usually use an MSE or a misclassification rate, depending upon whether you have a regression model or a classification model. But that's done on the test set or the validation set. Oops. Oh, well, something didn't come out right. We take the whole set, that's this here, okay, and we split it into two parts, a validation set and a test set, or a training set. An example, automobile data. Let's say we want to compare a linear versus a higher order polynomial in terms of a regression. Randomly split 394 observations, this is in the ILSR book, into two sets, a training set containing 196 of the data points and a validation set containing another 198, okay? And so we look at the mean square error with a single split and a mean square error with many splits. Here's what the problem is with this. The validation estimate of the test error can be highly variable depending on precisely which observations are included in the training set and which are in the validation set. We hope that randomization handles that, but you could be unlucky. Okay, you could get all of the women in the test set and all of the men in the training set. And then when you train, if gender matters, you might have a big problem. Low probability event that would happen. Yeah, but what if it was 60% of the men were in one and 40% of the women were in the other? You would just have an imbalance, and it's the drawback of that. There's a way around this, you'll see. In the validation approach, only a subset of the observations, those that are included in the training set, are used to fit the model. This suggests that the validation set error may tend to overestimate the error for the model fit. Anybody know why? It's because you have fewer observations in the validation set than you would have if you use the whole model or all the data. So we tend to overestimate the test error relative to a model fit on the entire data because we have fewer observations. This brings us to something that we're going to use all quarter. And it's one of the more important things in machine learning. And I bring it up early on because I want to use it over and over and over again. It's so-called KFold Crossvalidation. It's widely used for estimating test error. okay? The estimates can be used to select a best model and to give an idea of the test error for the final chosen model, and one that is not too far off. The idea is to randomly divide the data into 12 equal size or nearly equal size parts, leave out one of the parts, say part K, and fit the model to the other K-1 parts combined, and then obtain predictions for the left out K part. And then repeat that for each one of the parts left out, okay? So divide your data into 10 parts. Take out the first part. You have 9 other parts. Train your model on that. Do your predictions on the first part. Hold those predictions and their errors aside. Then take the second part. Put the first part back in. Train the data on parts 1, 3 through, say, 10. And predict in the second part and calculate the mean square error for that second part and set that side away. And do that for each one of the K parts. Okay, so divide K into roughly equal parts. Okay, so we have a validation part, a train, a train, a train, and a train. Okay, so these are all roughly the same size. We hold one set out and we train on all the other pieces. So let the K parts be C1, C2 through CK, where CK denotes the indices of the observation in part K. Okay, so you have 500 observations. You randomly divide them into 5 parts. The indices that are in the first part are C1. The indices in the second part are C2, and so on. There are NK observations in part K. Okay. Now, why aren't there 100? Okay. Well, if you have a N, a big N, that is a multiple of 10, it works out fine. But what if you had 299? You can't get exactly equal parts. You get one of them is going to have 49 and the others are going to have 50. You can always divide the data up in such a way that no part has more than one or less than one of any other part. And I won't bother proving that to you, but you can do that. So then what we do is the following, okay? I take the first group, I hold it out, okay? I train on the second part, that's C2 through CK. I predict on the first part, and I calculate the mean square error from that. So that's going to be MSE1. Then I'm going to take the second group. I'm going to train on everything except the second group. And then I'm going to fit the model to the second group and calculate the MSE. That's going to be MSE2. And I'm going to do that for all K parts. Then I weight each MSA by NK over N. Now, in fact, I'll say this in a minute. And then I sum them up. So this is a weighted average of the mean square errors of each of the K models, or each of the K parts. Okay, what's the MSE? The MSE is the model fit with all the other observations except those in CK. So we fit that model, for each observation in CK, and we use the Y's in CK. And now, if n is a multiple of k, okay, then nk is just n divided by k, and then this simply becomes the sum, each of the MSEs divided by k, or the average MSE over the k folds. Does that simplify the CV formula? Yes, it does. And so what I tend to do is I think of the CV as simply the average MSE from the K parts. So MSE for each one of the K folds and average them. As I said, it's just a little bit off because you don't necessarily have the case that you can get actually an equal number in each fold. Okay. So what happens when you do this? Okay. Here in the blue are the actual MSEs. Okay. And here are the tests, and you see they're very, very close. You don't get the overfitting that you get from using things that are in sample. I didn't do the animation right here, sorry. Since each training set is only k minus 1 over k as big as the original training set, the estimates of the prediction error will tend to be biased upwards. We talked about this. This bias is minimized when k equals n. That is, I drop one observation out, okay? So this would be, it's called leave out one cross-validation. So what I do is I take the first observation, I pull it out, I estimate my model with everything else, and then I use that to predict the first observation. Then I drop the second observation out, putting the first observation back in, retrain the model, predict the second observation based on that, and get an error. And do that for all n observations. And that tends to be the leave out one cross-validation. It turns out that estimate has a high variance. It has some other problems in that you have to run the model n times, where n is your number of observations. However, we'll see in certain regression models, there's a slick formula that makes it really fast. Okay. So if we leave nothing out, we have a high bias, we overfit, but a low variance. If we do leave out one cross-validation, we have the bias is low, but we have a high variance. And what we have found that k equals 5 or 10 provides a good compromise. I am sure somebody is going to write a paper that tells you that in some cases it should be 15, in some cases it should be 3, in some cases it should be 35. Those papers haven't been written yet. There's a lot of nervousness with KFold cross-validation because oftentimes, as you will see, you choose your tuning parameter to be the one that minimizes a certain cross-validated mean square error or error rate. And so that means you're kind of using your test data to train something. And so there's nervousness about this, but we go ahead and use it. We will later on in the course use Viktor Chernozhukov's high dimensional modeling HDM-R package. He's quite negative on KFold cross-validation, although he does use it, as do we all. He has a plug-in formula for a certain tuning parameter, and that is conservative and it works, but it only works for that kind of model. That will be a LASSO model. More generally, you can't figure out what the optimal is, and so cross-validation is what you're left with. Okay. Oh, again, I have problems with the animation. So for cross-validation, we do the same thing. We split the data into K parts. We compute the CV as the weighted average of the errors, where the errors are the misclassification rate. Recall, this is the number in the test set that we misclassify divided by n. And so this is the average misclassification rate in fold K. We do that for each K. We put it in here, and we take the average. We can also calculate an error measure for this average cross-validation rate. And it's simply given by this formula. It's the error minus the average error. So average up all of these errors, square them, sum them, and divide by K minus 1. That's the usual formula for a standard, and take the square root. That's the usual formula for a standard error. It turns out it really isn't the standard error of the CV. The standard error for the CV is much more complicated. But it turns out it works well for what we use it for, and that's for ranking models. So even if it isn't the correct CV, it will help us in ranking models from most accurate to least accurate. Okay. So what does this have to do with anything we've done so far? Well, we just estimated nearest neighbor regressions and nearest neighbor classifications. And when we did a nearest neighbor classification, we estimated a probability using nearest neighbors, and then we used the Bayes classification rule. How do we choose the number of neighbors? If we have a large number of neighbors, we tend to overfit. If we have a few nearest neighbors, we tend to underfit. With a large number of neighbors, the variance is pretty small, but the bias is pretty bad. That is, if we change the data a little bit, our classification model isn't going to change very much, but it's going to be badly biased. In contrast, if the number of nearest neighbors is small, as the data changes, we're going to find that our estimates, our predictions of what class the same person is in is going to change quite a bit. So how do you choose that number of neighbors? Remember I said the number of neighbors is a tuning parameter, also called a hyperparameter. and we don't know what it is, we have to, quote unquote, estimate it somehow. We have to figure out what it is. And what we're going to do is we're going to use KFold Crossvalidation. This is going to be the second big tool we work with in this course. The first one was the idea of having a test set and a validation set. The second one is KFold cross-validation. And of course, the whole idea of, so I guess it's the third one, the bias variance trade-off. Okay. So, an aside, cross-validation, right and wrong. Okay. Let's say you start with 5,000 predictors and 50 samples and find the 4 predictors that have the largest correlation with class labels. Okay, you just do that. Or alternatively, you start with 5,000 predictors and you find the 4 predictors that have the highest correlation with the dependent variable if you're doing a regression. Okay. And then apply KNN using only those 4 predictors, or use KNN regression using only those 4 predictors. So 2 steps. First, I reduce the number of predictors, and then I do KNN. How do we estimate the test performance of this classifier or regression? Can we apply cross-validation in step 2, forgetting about step 1? And the answer is no. It ignores it in step 1. The procedure already saw the labels of the training data, or already saw the targets in the training data, already saw the dependent variable, and it made use of them. That's a form of training, and it has to be included in the validation process. So there's something that people call pre-processing the data, and people do this all the time. One has to be very, very, very careful that one pre-processes the data, one hasn't entirely screwed up the process. Okay? It's easy to simulate realistic data with class labels that are independent of the outcome, so that the true test error is 0, but the CV test error that ignores step 1 is 0. That is, you can pre-process the data in such a way that you can get your cross-validation error equal to 0, even when the true test error is 50%. So, when you do a multi-step estimation and you're using cross-validation, you have to use the cross-validation on the whole process. That is, your estimation is going to be from getting the data all the way through to getting the estimates. And you can't go 3/4 of the way through the process and then at that point say, here's our data that we're going to use, and do cross-validation after that part. It simply won't work. This error is often made in genomics papers. They're just rife with exactly this error. They do a bunch of pre-processing, and oftentimes it works like this. You're the research assistant for the lab. You're the statistician for the lab. You created these data. The lab director helped you decide what went in there, what didn't go in. You got a nice cleaned up set of data. And then she makes it available to the rest of the discipline to use. The problem is you did a lot of pre-processing, and that pre-processing oftentimes has reduced the error and will lead you to overfitting. And as I said, this happens in genomics papers all the time. Doesn't happen in economics papers. Why? Because we are only recently using these tools, but it's going to happen. So wrong is to apply cross-validation in step 2, and right is to apply cross-validation in step 1s and 2s. Wrong is to apply cross-validation in the latter steps. Right is to apply cross-validation to all steps. So that means when you split your data into the folds, it's the original data that gets split into the folds, not the post-processed data. Okay, so back to parametric models. And by the way, we're going to go, when we do K nearest neighbor estimators again, which will be later in the course, we will go in detail about using KFold cross-validation to estimate how many neighbors one should use. Similarly, when we try to decide, well, I won't say that yet. So I want to go back now to parametric models. I gave you a flavor of the non-parametric models. They tend to be relatively uninterpretable. They tend to be quite flexible. They tend to have high biases. One of the problems you'll run into with the K nearest neighbor, which sounds like you should use them all the time, is they suffer from what's called a curse of dimensionality. That is, if you have more than 2 or 3 independent variables, the nearest neighbor stuff fails disastrously. Okay, so we talked about classification models, 2 classes with a vector of features. Okay, we want to predict which class based on X. We did it with K nearest neighbors. And as I said, it will turn out to be useless for more than 3 features. Okay. Here, I'm going to discuss a general parametric framework that will work with many different kinds of problems. So I'm going to introduce you here to something called the logistic regression model. But what I'm really talking about is a general approach to modeling. And it's modeling from very simple models to very complex models. I'm going to do it with a logistic regression model, but I will give you a homework at some point that asks you to do things, the same thing with a standard regression model. And you will see exactly what I'm talking about, okay? Recall, we estimate the probability for each class, and we assign to the class with the highest probability. So if your characteristics are the vector X, and I want to know which class should I assign you to, are you somebody who has COVID? Are you somebody who doesn't have COVID? I have a probability model for what's the probability of somebody with characteristics X having COVID. If the probability of having COVID is higher than the probability of not having COVID for your X, I assign you to COVID. If the reverse, I assign you to not COVID. That's the Bayes classification rule. Something seems to be wrong with my, there we go. There we go. Here's a simple model. This is the simplest kind of model. Think of COVID. So yi is 1 if you have COVID, 0 otherwise. And we're going to make it binomial. That is, you have COVID with probability P, and you have not COVID with probability 1 minus P. Okay. Now I'm going to observe a random sample. okay? No features for now. So let's say they're in the background. I've observed whether people have COVID or not COVID. I also know what their characteristics are, but I'm not going to pay any attention to those right now, okay? So I observe only a random sample of the indicator 1 or 0, you have COVID or you don't. More specifically, say that my sample turns out to be this. I get has COVID, doesn't, has COVID, doesn't, has COVID, doesn't, has COVID, has COVID, has COVID. So I have 10 observations, and this is what I have. And I'm going to let Y be my vector of observations. So this is a vector, okay? And I'm going to ask the question, given I know P, or assuming I know P, what is the probability that I observe Y? Okay, and I'll just talk about what's the probability I observe a 1? Well, it's P. What's the probability I observe a 0? Well, that's going to be 1 minus P. What's the probability I observe a 1 and a 0, provided they're independent? That's why a random sample is really important here. Well, the probability I get a 1 and a 0 is the probability I have a 1 times the probability I have a 0. So it's going to be P times 1 minus P. And now what we're going to do is we're going to go through this whole vector Y and figure out what's the probability of having observed Y. Another problem with my animation again. So the probability of Y is the probability that Y equals 1 times the probability Y equals 0 times the probability that Y equals 1, and so on. And it's Y1, Y2, Y3 to Y10. Remember, they're identically distributed, so they have the same probability, okay? If they weren't identically distributed, you could still multiply them, but you wouldn't have the same probability. So the probability that Y equals 1 is P. The probability that Y equals 0 is 1 minus P. Thus, the probability of this sequence is this probability, which we talked about here. Let's plug and chug. P, 1 minus P, P, 1 minus P, etc., P, P, P. So here we go. P, 1 minus P, P, 1 minus P, P, 1 minus P, 1 minus P, 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 P. Okay, simplify that. You get P to the 6th, 1 minus P to the 4th, P to the number of 1s. 4 is the 1 minus P to the number of 0s. And notice that 6 plus 4 equals 10, the number of observations. Okay. You know, this is a pain in the butt. You know, let's say I have a couple million of these. This is going to be kind of hard to do. What's even worse is I want to talk about this stuff theoretically. How do I do that? Well, I'm going to give you a trick. Ah, darn it. Yeah, none of my animations work. So the probability that Y equals YI, so let's say we're looking at the first one, is PI. Okay. I claim that PI can be written in the following way. PI can be written as P to the YI, 1 minus P to the 1 minus YI. Actually, this should not be here. So this is only true if YI is equal to 1. So let's go back here. So PI, when yi is equal to 1, pi is p to the yi, 1 minus p to the 1 minus yi. That's equal to p, yi is equal to 1, 1 minus p to the 1 minus 1. Okay, so that's p to the 1, 1 minus p to the 1 minus 1, or p to the 1, 1 minus p to the 0. Anything to the 0 is 1. And so this is p times 1. Now, let's look what happens when y is equal to 0. Okay. Oh, I guess pi is right here. Never mind. So now pi is p to the yi, 1 minus p to the 1 minus yi. When y equals 0, yi equals 0. Okay. Notice up here, it was equal to 1. 1 minus yi is 1 minus 0. That's 1. Notice here it was 0. And so I get p to the 0, which is 1. 1 minus p to the 1, which is 1 minus p. And so regardless of what y is, the pi is correct. That is, the probability of seeing yi is p to the yi, 1 minus p to the 1 minus yi. So this is a trick that we will use quite often. Another problem. Okay. The probability of y is the product I equals 1 to n of the pi's, product I equals 1 to p yi, 1 minus p, 1 minus yi, and that's true regardless of what y is. So remember, y is the vector y1, y2, y3, y4, dot, 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 up to yn, okay? Now I'm treating this as a function of p, okay? It's a function both of the data and of p, but I'm now going to treat it as a function of p with y's known. And this is called the likelihood. This is the probability we would observe y when the probability model is as stated and is a random sample with, yi equal 1 with probability p and yi equals 0 otherwise, okay? Different probability models will give us different likelihoods, but the point here is now we have the data and we ask the question, the data are correct. We know what they are. Let's write down what's the probability of seeing those data as a function oftentimes of unknown parameters. Here it's p. Later on, there'll be regression type parameters. Different models will give different probability, different likelihoods. We'll see that the standard ordinary least squares regression comes from a likelihood where the errors are normal. It doesn't have to come, that isn't the only way it can happen, but it is a way that it can happen. Okay, so we have something called the likelihood. This gives us the probability that we observed what we observed. So this is going to lead to a new method of estimation. Currently, we have two. You have least squares from 482, and we've talked about k nearest neighbors. That is, you take the k nearest neighbors and you average them up. And now we're going to add, come on. Oh. I think I know what happened. In my animations, I tried to put some things swirling in and the like, and I think this just doesn't like it, so I won't do it anymore. We're going to add something called maximum likelihood, and this was introduced by R.A. Fisher, who's one of the fathers of statistics, somewhere between 1912 and 1921. The reason we say somewhere in there is he kind of changed his mind about what maximum likelihood, what the basis of maximum likelihood was, oftentimes during that period. And some of the justifications just don't make any sense. Didn't make any sense back then, but he was inventing this as he was going along. And as I said, he's one of the fathers of modern statistics. Maximum likelihood. Loosely, what we're going to do is we're going to choose for P that value which makes what we saw the most likely one we would have seen. What do I mean by that? Well, we saw a bunch of ones and zeros. We have the likelihood as a function of the probability. And I say, what probability P is the one that would most likely, with highest probability, generate the data we saw? Okay, that is, we choose our P hat to maximize that likelihood. We say, what is the most likely P to have generated this? Now, we have to be careful there because P is not a random variable. Okay, so it's not either likely or not likely, but it's the one that makes what we saw the most likely to have been seen. Notation. Darn it. Okay, so here's our likelihood. Okay, this is, if we knew what P was, this is the probability we saw Y1, Y2, Y3, Y4 up to Yn. Okay. Argmax. This is the argument, P. All right. And so this says, find the argument, P, that maximizes this. So P hat is the P that maximizes this function. Now, I could also ask the question, and we'll be interested in this later, what is the maximum value of this? And that would just simply be the max. So argmax says we want the argument that does this. Max says we want the value of the maximum. So we find the P hat that maximizes this. Okay. We're going to denote this likelihood function by LP. So as it turns out, there's a whole theory for likelihood functions. That is, I don't have to know the specific form of the likelihood function to answer all sorts of questions about it. And that gives us a very powerful theory. So somebody says, I estimated this by maximum likelihood. And you go, oh, what are its properties? And you go, it's maximum likelihood. Or in the case of a regression, you say, I have a regression that satisfies the Gauss-Markov assumptions. And somebody says, well, so what are its properties? And you go, best, linear, unbiased, right? And so we'll have something like this for likelihood functions. For likelihood functions, we'll have something like unbiasedness called consistency. We'll have something like best. We'll have something called efficiency. And it turns out in large samples, the p-hat is always going to be approximately normally distributed. So that's going to be useful to us. So how do we find this maximum? Okay, and we're going to do it for this case, but I'll mention that by and large, this case and the regression are the only cases where you can come up with closed forms. For most things, we're going to have to do what's called numerical optimization, and that's going to be next time's lecture. And once we have that, we can start learning about the R package GLM, which is going to be one of our workhorse packages. So the thing to notice about LP here, this probability function, is that it's univariate. It only depends upon P. Darn it. How do we maximize a univariate function? Okay. If it has a minimum, we take the derivative and set it equal to 0. Okay. And then solve. So this is first year calculus. Here's the likelihood. We take the derivative of the likelihood with respect to P. Okay. And we set it equal to 0. Now, this derivative can be taken, but it's a bit of a mess, okay? In general, you don't want to deal with products unless you have to. And so what we're going to do is we're going to try and find a different form for this likelihood. And this is going to be more of a digression on optimization. Those of you who've taken Melissa Knox's ECON484 have probably seen this. Any of you who've taken a optimization course have seen what I'm going to talk about now. But this is one of the tricks of the trade in optimization, a useful theorem. Darn it again. Whoops, let's go back. Let H be a function, a monotonically increasing function of a scalar. And I'll talk about what monotonically increasing is in a minute. Then the argmin of LP with respect to P is the same as the argmin of H applied to LP. That is, if you solve this problem, take the derivative of LP, set it equal to 0, and solve for P. Or you solve this problem, take the derivative of H of LP with respect to P and set it to 0. You will get exactly the same P regardless of which problem you solve. So what we want to do is we want to find a transform problem that makes the algebra easy. There's an old saying, the only good statistician is a lazy statistician. One of my uncles who's an engineer, the first time he heard that said, no, the way we learned it is the only good engineer is a lazy engineer. And I guess it just depends on your profession. You want things that are simple and easy, but get to the answer. Okay. So what are monotonically increasing functions? Their derivatives are always positive. What do they look like? Here's some. Okay. Here's the logarithm. Here's e to the x. I forget what this is. I think this may be x squared. And I forget what this one is. What happened to my, yeah, okay. So we had e to the x, we had log x, we had this function, which is going to become one of our workhorse functions. And what they all have in common is they are increasing. This is increasing, but it flattens out at 1. Technically speaking, if it flattens out, it's not monotonically increasing, and so you probably wouldn't want to use any function that flattens out. I just wanted to introduce that functional form now because we're going to be using it all of the time. So, which one makes our life easier? Remember, we have a likelihood that is a product. It's a product of, let's say we have 100,000 observations. It's a product of 100,000 probabilities, okay? We don't want to use products. Logarithms convert products to sums. Sums are easy to work with. The derivative of a sum is the sum of derivatives. So let's try that. Whoops. Okay. So we have little LP is the log of the likelihood. It's called the log likelihood. Okay. It converts products to sums. So sum log of PYI plus log of 1 minus P to the 1 minus PI. And then we recall that the log of P to something is the something log P. Log of 1 minus P to something is the something times 1 minus log P. Take the derivatives of this and set it equal to 0. So notice here we're going to have a derivative, and we have the derivative of a sum. Derivatives of sums are pretty easy to take. We solve the first order conditions. That is, setting that equal to 0, that's called the first order conditions, and we want to set that equal to 0. So we have the sum yi derivative of the log plus 1 minus yi derivative of log of 1 minus p. The derivative of log p is 1 over p. The derivative of log 1 minus p is minus 1, because of the minus here, times 1 over p. And so our log likelihood becomes the summation yi times divided by p minus 1 minus yi divided by 1 minus p. And we want to set that equal to 0. Darn it. So 1 minus p times the sum of the y's. 1 over 1 minus p, this should be 1 over p. 1 over 1 minus p times the sum of the 1 minus y's. Okay. Note, y is equal to 1 only if it's a success. okay? And so the summation of the yi's is the number of successes. So we're going to let ns become the number of successes. And so this becomes ns. And then I want to go through this in a little detail because a lot of people make mistakes on this. So let's just leave our minus sign out here. And let's do the sum of 1 minus yi. That's the sum of 1 n times minus the sum of the yi's. Now the sum of the yi's is what? It's ns. What's the sum of 1 n times? It's n. It is not 1. It is n. And I'll just tell you, the reason I do this is I've seen so many people make mistakes on this that I just go through it in great and gory detail the first time we see it. By the way, I don't go through things again after you've seen them. So this becomes 1 over p ns minus n minus ns times 1 over 1 minus p equals 0. And now we solve for p. And what does it give us? It gives us p hat, this is our maximum likelihood estimator, is ns divided by n. And what's that? That's the sum of the yi's divided by n. That's the average of the y's. By the way, when we first started talking about probabilities, we said, well, the probability is an expectation. We estimate expectations by using sample averages, and we get the same thing here again. Okay, go back into your notes. You'll find this in the first lecture. Oftentimes, the maximum likelihood will give you an estimator you already know. But what it means is, since there's a general theory for maximum likelihood estimation, which we will talk about, it means that every time you get such an estimator, you don't have to go back and work out in detail what the principles are, or what the properties are. You'll know automatically. You'll say, oh, it's a maximum likelihood estimator, so it has these properties. So oftentimes you'll have an estimator you already know, or one that makes independent sense, that when you look at it, you go, that makes a lot of sense to me. I can see why I would do that. One last detail. Setting that derivative to 0 and solving is insufficient. Why? You might have gotten a minimum. Remember that when you set the derivative equal to 0, you could have gotten a maximum, you could have gotten a minimum, you could have gotten a flat spot called a saddle point. You also could have gotten local maximums or local minimums. Imagine a double humped mountain, well, like Mount Rainier. There's Little Tahoma and Big Tahoma, and you might be up in the top of Little Tahoma in the flat spot, and you say, oh, I found the maximum. No, you just found a local maximum. And if you go in between them, where you're in the U-shaped valley, you would have a minimum. And you would have a flat spot there. The derivative would be 0 as well. And so, to know whether you have a maximum or minimum, you need to know more. That brings us to second order conditions. Second order conditions are going to be important in this course. Okay. You have a local minimum if the second derivative is negative. You have a global maximum if the second derivative is everywhere negative. So if you calculate the second derivative at every single point and everywhere it is negative, it turns out you will have a global maximum. Such a function is called concave. And we'll spend a lot of time talking about concave and convex functions, if for no other reason that then when we work with neural networks are horribly non-concave or non-convex, depending upon whether you're looking for a maximum or a minimum. Oops. Okay, so you have a local maximum if the second derivative is negative at p hat. You have a global maximum if this second derivative is negative everywhere. Let's see if I have the next term in there. Yes. Okay. So if you take that second derivative, you have a minus, and I want you to work this out yourself. Take the derivative of this with respect to p, and you get this number. Okay. Everything in the sum is positive, and so the sum is positive. That is, yi is, well, positive or non-negative. Yi is either 1 or 0. And so this could be 0, in which case this is 1. Alternatively, if y is 1, then this is 1, this is 0. The probabilities, unless there's 0 and 1, are positive. So everything in the sum is positive. The sum is positive, and so minus the sum is negative. Okay? So the second derivative's everywhere negative, so the maximum likelihood estimator exists, and because it's a global maximum, it's unique. In grad school, you're going to have to do this a lot. What's relevant here is you'll read papers and they'll spend a lot of time going through to showing that their function has a unique optimum, or if it doesn't have a unique optimum, that it doesn't matter that it doesn't have a unique optimum. Okay? And sometimes 3/4 of the paper will be about that. For applications, you're not going to want to spend a lot of time with that. If you're eventually going to be an inventor of tools, which I hope at least some of you are going to end up doing, then you'll have to pay attention to this. Nonetheless, you're going to have to read theoretical articles. Why? Because you want to be the first person using the theoretical stuff. You want to be the one that they go to and they say, how do we do this? And you say, hey, there was this new method I just read about. Even if you couldn't invent it yourself, you ought to be able to apply it, or we want you to be able to apply it. And so that's why it's important you understand these terms, even if you can't in detail go through them. Alas, this is one of the few times we can ever work out the maximum likelihood by hand. It's basically when it turns out to be a mean, we can work it out by hand. Other than that, we just can't. Okay. The problem is this is very inflexible. The probability is fixed. So now we're going to go to the other extreme. So this assumes that everybody in the population has the same probability of having COVID. And we already know the doctors are saying, look, you know, if you're a little kid, if you don't have any underlying conditions, not only are you unlikely to get COVID, but if you do get COVID, we won't even know it because you won't show any symptoms. And if you're older but have some underlying problems, you might show it. You might get a little bit. It'll kind of be like a cold. Even if you're my age, if you're in your 70s, you have to worry a bit. But if you don't have any underlying conditions, you don't have diabetes or heart disease or anything like that, and I guess you're not the Prime Minister of Great Britain, then you don't have to worry that much. But if you have any underlying conditions in that, the probabilities are different. And if you're over 50, the probability you get COVID seems to be higher. And if you're over 70, it seems to be even higher, even if it's not going to be fatal. So just as a matter of common sense, it doesn't make sense to say everybody has the same probability for COVID. Let's say we change it from the probability of COVID to the probability people buy a big screen TV. Not everybody's going to have that same probability, not everybody in the population. You might think wealthy people are more likely to buy it if they don't have a big screen TV. People who don't have a big screen TV are more likely to buy it, and so on. So the idea that the probability would be constant in a population really doesn't make any sense. Similarly, I want to predict weight in a population. I go and I say, here's the average weight, and that's my prediction for everybody. And you just look around and say, well, gosh, I can just look and see that's not true. I can see things that are easily observable that would give me a better prediction, or that I could use to make a better prediction of what weight is. And so the idea that the expected value is fixed just doesn't make any sense. Recall that the probability is an expected value. So let's go to the other extreme. This is called a saturated model. Uh-oh. Okay, we lost. Oh, there we go. Okay. So a binomial model with all the probabilities are different. That is, yi equals 1 with probability pi, 0 otherwise. Okay? So everybody's going to have a different probability. The log likelihood is formed the same way, okay? But now it has n probabilities to determine. That is, the log likelihood is yi log pi, not fixed p, pi. 1 minus yi log 1 minus pi, not fixed p, pi. Sum that over, and I can tell you that this does not have any meaningful solution if it has any. One possible solution is pi simply equals yi. The problem with that is you can't take the log of 0. And so if yi is equal to 0, the pi can't be 0. So that's why it has no meaningful solution if it has any. You can play with L'Hopital's rule and get something that looks like it might make sense, but it really doesn't. Basically, this problem has no solution. You will find that's the case generally if you have as many or more unknown parameters, pi, as you have observations. Here we have exactly as many parameters. We have n parameters pi as we have observations. And in a case like that, you're going to find no meaningful solution if it has any solution at all. And this isn't simply with this model. It's saturated in the sense that it has as many parameters as parameters to be estimated. And that's the other extreme. It certainly makes sense that everybody has a different probability, but we can't estimate the probabilities. What we want is a less complex model. Let's assume now we have the features for each observation, and we recall that yi can always be written as the expected value of yi given x plus an error. When we did regression, how did we model the expected value of y given x? We wrote it as yi equals xi transpose beta plus an error. That is, we used a linear model to predict the expectation. So let's try that. Okay, this is called the linear probability model. That is, recall that if y is 0, 1, the expected value of y given x is the probability that y equals 1 given x. Okay, so if y is a 0, 1 random variable and y equals x beta plus an error, and the error has a 0 expected value given x, or we assume that, then x transpose beta has to be the expected value of y given x, and it has to be the probability. And so we're saying the probability is linear in x's and in betas. Okay. This is a legitimate model, and it is sometimes very useful. It's very useful because you can do ordinary least squares. And it's a lot easier than what we're going to end up doing when we do maximum likelihood on the generalizations of these models. Okay. You will still get unbiased estimates and predictions. That's good. But, darn it. The errors are heteroscedastic. So that's the first thing. And so you're going to lose efficiency. Want you to recall this, that the variance of y given x is the expected value of yi squared minus the expected value of y squared. The expected value of yi squared given xi minus the expected value of y given xi squared. That's one of the formulas for a variance, relating a variance directly to the first and second moment of the distribution of y. But, and I mentioned this in passing before, but I really want to harp on it now, yi equals yi squared. Why is that? It's because y is 0 or 1. 1 squared is 1. 0 squared is 0. So y squared is y. So we plug that into the formula. Now we have that the expected value of yi squared given x is the expected value of y given x, okay, which is pi. We have the expected value of yi given xi squared, that's pi squared, and given our model, this is xi beta 1 minus xi beta. Right. I just factored out the p. Okay. What that means is the variance is not constant. The variance of y given x depends upon x, and so your model is heteroscedastic. You don't have best. You still have linear. You still have unbiased. You have to either do generalized least squares or use a heteroscedastic consistent covariance matrix. Okay. Second problem. Darn it. Nothing restricts x transpose beta to be between 0 and 1. Okay, so when you predict out of sample, you're going to get probabilities that are negative and probabilities that are greater than 1. It turns out you can fix that linear probability model. You set pi equal to the minimum of 1 and the maximum of 0 and the probability. So the maximum of 0 and x beta is going to be x beta, or it's going to be 0. Okay. If it's 0, then the minimum of 1 and 0 is 0, and p is equal to 0. Let's say it's not 0, then it's xi transpose beta, and I want the minimum of those two. If xi transpose beta is less than 1 but greater than 0, then xi transpose beta is the minimum of 1 in that, and pi becomes xi transpose beta. If xi transpose beta is greater than 1, the minimum of that and xi transpose beta is 1, and so this becomes 1. So this forces it to be between 0 and 1. It turns out there is a paper by Viktor Chernozhukov, you'll hear about him a lot in this course, where he shows that in fact that actually fixes the linear probability model, that in fact is a principled thing to do, and it actually reduces the mean square error. So if the prediction is greater than 1, you set it to 1 or slightly less. If it's if it's negative, you set it to 0 or slightly greater. And then you do generalize the weighted least squares. So if you're going to do generalize the weighted least squares, that's when you have to do the slightly less and slightly greater, or you're going to get 0 variances. And with 0 variances, you can't divide through by 0 to do the weighted least squares. Or you use a heteroscedastic consistent covariance matrix for the coefficient matrix. None of this is really satisfactory, and it makes it really hard to interpret if you are changing x, and it would send you above 0 if you're changing x, and it would send you above 1, or you're changing x and it's sending you below 0. So it's really hard to interpret. Nonetheless, it tends to be useful because to rank things correctly in terms of how likely they are. Okay, let's see if we can fix the out of 0, 1 range problem. Okay, let's just start there. Darn it. Okay. We have y equals e of y given x plus an error, which equals pi plus an error. We want the pi to depend on X and range between 0 and 1, okay? That is, we don't want that to get bigger than 1 or less than 0. Okay. Come on. And so let us try P of X equals some function of X beta where F is an ogive or an S-shaped function that is monotonic increasing and ranges from 0 to 1. Cumulative distribution functions are such functions. So if you took F to be the standard normal, the model would be called a probit. Whoops. Yes, over here. So if this were the cumulative distribution function for a standard normal, the model would be called a probit. If F is taken to be a logistic, and we're talking about the logistic in great detail, then the model is said to be a logit among economists. We call them logit models. And statisticians and ML scientists call them logistic regressions. So if I say I do a logit around a statistician or an ML scientist, they think I'm talking about doing a transformation, which we'll talk about later in this lecture. Logistic regressions, economists used to model growth. And so we used to do linear regressions that modeled the logistic growth path, and we'd say, oh, we did a logistic regression, meaning we did a standard regression that had the growth pattern to it. And it's one of those things where the terminology differed in different disciplines. Whoops. So for a normal, that distribution is given by this integral. Here's the density for a standard normal, and we integrate it from minus infinity to t with respect to s. It turns out this is a hard computational problem. It also doesn't have a closed form. This is one of those things that would be a trick question in a class where they said, okay, you know, find the antiderivative of this. You can't. Doesn't have a closed form. The logistic, however, whoops, don't want that. The logistic distribution has this form, however. 1 over 1 plus e to the minus t. I always write exp. That means e. Okay, so let's see what this function looks like. Okay. First, what happens if t is equal to infinity? If t is equal to infinity, exp to the minus t is what? It's 0, and so I get 1 over 1. So f to the infinity is equal to 1. Let's say t is equal to minus infinity. Okay. 1, 1, exp to the minus infinity is going to be exp to the infinity. So 1 over 1 plus infinity is 0. Of course, you have to take a limit to do that right. But it basically says f of t is equal to f of t is equal to 0 at minus infinity, and take the derivative and show that the derivative is always positive. So here is the logit or the logistic probability model. This is the model that early on people used, Netflix used, anyone who is going to predict whether people were going to buy things or not buy things. It's what the bioscientists still use, although they use the more advanced stuff we're going to talk about in this course as well, still use to determine whether somebody likely has diabetes, has cancer, has COVID, has the flu, and so on. And so our model yi equals 1 with a probability given by this, and this thing, no matter how you take x and beta, will always be positive and be between 0 and 1. And it equals 0 otherwise. Okay? 1 minus pi, where this is taken as pi, is 1 minus that probability. Now, ordinarily, I wouldn't state that, but it turns out that this has a very useful form that won't leap out at you unless you do some algebra, and I want you to do this algebra, but it turns out 1 minus p is exp to the x beta minus x beta divided by 1 plus exp to the minus x beta. So both pi and 1 minus pi have the same denominator. That's going to become crucial later on. Darn it. So our log likelihood, remember what the log likelihood is. It's yi minus log pi, 1 minus yi log 1 minus pi, summed over the i's. And in the saturated case, these pi's are the same, are different for every observation. Now we're adding some structure. We're saying that the pi depends upon the data in this way. Okay, and the thing I want to point out here is, let's say you had 20 features, okay? You only have 20 unknown observations here, parameters here. And so you have n observations and 20 parameters. So if n is a lot bigger than 20, you're home free. And we now have probabilities that change with the x's. These might have things like gender, age, dummy variables for various kinds of prior conditions, underlying conditions, maybe a dummy variable for under 20 and a dummy variable for over 65. And you would take that information from has a dry cough and plug that in there, and I would want to estimate these weights. I would want to estimate these weights. Why? So that I could estimate for you your probability. If your probability is greater than 0.5, then I'm going to say you've got COVID, you likely have COVID. If it's right around 0.5, not really likely. But if it's like 0.9, I go, you really probably have it. And let's say it's 0.99, I would say, you've almost certainly got it. Okay. Turns out that this simplifies, and I want you to do the algebra for this. I want you to show that this is in fact equal to this. Okay. So we have the yi's times the xi's here summed times beta. And then we just sum up I equals 1 through n, the log probabilities. And that's what our log likelihood is. And what we're going to want to do is we're going to want to choose betas to maximize this, okay? This cannot be done by hand. And we're going to need to learn some numerical optimization. Now, it's going to turn out that GLM, one of the packages we're going to use, has a numerical optimization package built into it. The problem is numerical optimization is a lot more things that can go wrong with it than doing a regression. What can go wrong with doing a regression? The only thing that can go wrong with doing a regression in terms of getting estimates for the betas, the only thing that can go wrong is you have multicollinearity. If you have multicollinearity, then you won't get an answer. Okay? With numerical optimization, all sorts of other things can go wrong. You need to know how to deal with them because you will run into them. You will get non-convergence. You will get the Hessian matrix is too flat. You will get stop too soon, which may be different than non-convergence, but you won't know. You will get situations where you don't get unique answers. And you will control those in GLM by going into the guts of the optimizer and changing some of the parameters. You'll change the convergence rule. You'll change, and you'll learn what all these things are. You'll learn the method. So there are different methods for doing numerical optimization. You know, some are really fast except when they fail. And so you try those, and if it fails, you go, oh, that failed. Now what do I do? Well, then you try one of the other ones. Well, what are the ones that are likely to work? Well, you can try them all, or maybe you'll have some instinct, or you'll know something about the problem that'll say, yeah, I want to use this one, I want to use that one. And as you go further into this, you're just going to have to teach yourself numerical analysis, because this stuff goes wrong all the time. We probably at Amazon do 1 million, 2 million optimizations of the type we're talking about a day. Okay. Let's say 10% of them fail. That's a huge number. And so our data scientists have had to learn how to program things to handle situations when they fail. And you maybe can cut that down to a few hundred failures a day. It's still the case. You've got a failure and you've got to get some output for your boss. And so you've got to sit there and you have to know how to change the numerical analysis routines. Okay. Our packages that carry that out, we'll talk about them. Before we get to that, before we spend all this time learning numerical optimization for the logit model, we have to ask a question. Is this model interpretable? The whole point here was we were trying to come up with something that was kind of simple and interpretable. And we have to ask the question, is it in fact interpretable? If not, do we want to waste time learning how to estimate it? The answer may be yes. There may be reasons to learn, but for right now, we want to know, is this interpretable? Because while it's more flexible than the constant, it's less flexible than k nearest neighbor. So do we want to waste time learning how to estimate it? Okay. Now, interpreting logits. Now, this is a general approach to interpreting things. One way to interpret a model that works is to take a derivative with respect to a feature if the model is differentiable, or the difference, or take a difference if it isn't. Okay. But even then, all you get is this below. That is, this is how that changes when the other changes. So let's say you have a quantile, 0.9. Oh dear. Did I lose people? Hello?
Yeah, you're good.
I seem to have lost people. Or
We can still hear you.
okay. Hang on a second. Is the PowerPoint slide still up?
Yes. Yes.
Okay. Oh, there's it's working. Okay. Everything here went black, and I thought, oh, darn, is this Herbert telling me that it's 7:20 and I have to stop? No, I'm kidding. So you have a conditional quantile, you take its derivative, okay? How do you interpret that? What does it mean, the derivative of a quantile? I mean, I can say how much it changes. So let's say I say that the quantile changed by 0.01. What the heck does that mean? Okay. Sometimes the structure of a model will give an automatic interpretation, like it does in a regression. So in a regression, in a regression, you have x beta, and the betas are the effect of changing x on the expected value of y given x. So recall that p is the expected value of y given x, and that we're now saying it has this logistic regression form. Okay. Let's take the derivative. Okay. So we take the derivative of the probability with respect to x, and we get this. Okay. Make sure that you take this derivative and you convince yourself that this is the case, because you're going to use this a lot. Okay. So recall that 1 minus p was equal to 1 minus the probability, and had that form I told you was going to turn out to be useful. Okay. So it's exp over 1 plus exp. And now I want to go back to the previous page. Notice we have here an exp x beta minus x beta over exp 1 plus exp, and this should be in parentheses. So this should be a, let's see if I can do that. Sorry about that. That should be in parentheses. Okay. And so this equals E I'm just going to write E stuff over 1 plus E stuff times 1 over 1 plus E stuff times beta. Okay? So, just so you see that. Now let's go over here. And what this points out, whoops, is that dp dx is p 1 minus p times beta. Any of you recognize what p times 1 minus p is? Well, we're going to talk about it. It turns out that it's the variance of y. Okay, so I have p times 1 minus p, p minus 1 minus p, or p minus p squared, where p is e of x given y. So p times 1 minus p is e of y given x minus e of y squared. And we just showed that this is, in fact, e of y squared because y is 0, 1. So this says that dp dx is equal to minus the variance of y times beta. And imagine you're talking to your, let's say you have a brother or sister who's completely enumerate, maybe an English major. I get to say that because I was an English major before I did this stuff. And you say, so tell me about your model, and say, yeah, you know, when you change the amount of medicine I give you, the probability you're sick is equal to minus the variance of the dependent variable times beta. And you go, what? That doesn't mean anything. And you certainly wouldn't want to tell an enumerate boss or a federal judge or somebody like that that this is the explanation of the model. So look back in your notes and you'll see this. I do not know what happened to my animation here. I spent a lot of time, I thought, fixing it. I'm worried that the animation doesn't come through on Zoom. In which case, I'm just going to have to show the whole page. Okay, that's still not very informative. So solve for beta, and you say, okay, what's beta? Beta is minus the probability, the derivative of the probability of having COVID with respect to X divided by the variance. And you go, well, you know, that isn't very informative either. Let's do something else. Let's see if we can solve for X beta. And this is going to be a general thing we're going to try to do. Solve for X betas. Okay. You'll see presently why. I'm almost done here, and then I'll stop. Recall that P is 1 over 1 plus EXP, that stuff. The troublesome part of that is this part. It's the denominator. Recall that. So P and 1 minus P have the same denominator. P over 1 minus P, divide them through, and lo and behold, you get this. Take the log of both sides, and it gives you that. This is called the log odds. This is called the odds, and this is called the log odds. And so in the logistic model, the log odds, the log of the odds of having COVID over not having COVID, is a linear function of x and beta. And I'm going to stop there. Can everybody still hear me?
Yeah.
Okay. I'm going to stop here, and I will come back at this point and start next time. This is probably one of the key points of this lecture. That what I've done is I have found a transformation that is meaningful, that's a linear combination of the betas. And the only thing I'll point out is I have a function here, g, of the expected value and that's equal to x beta. Okay? If G were the identity, that would just be y given x, the expected value of y given x equals x beta. That would be a linear model. This is some function of the expected value is x beta. And this is the first of your generalized linear models that you're going to see. So most of the models that we're going to deal with that are parametric are going to be generalized linear models. That is, some transformation of the expected value of y given x is going to be a linear function of x beta. And all of a sudden, a whole bunch of what you learned about the linear model is going to be directly relevant to these nonlinear models. And in particular, you will find that interpretation becomes a lot easier. With that, I'm going to sign off for tonight. I'll assign some readings for next time online, and I hope this went better. I hope you guys, some of you have not been able to get to the downloaded video. Some of you have. I've tried to reproduce not getting it. I haven't been able to get it. Herbert, were you able to get it?
No, I cannot get the.
You cannot get it either.
Yeah.
Okay, I'll see what I can do. You know, I know that if you go and you just click on where it should be, it doesn't work. You have to go over to the Zoom panel and do it there. I will see if I can download it to the site. The problem I found was I wasn't able to download it to the site and load it back up because Google basically said, this is too big a file. You're going to have to put it in Dropbox or Google something or the other. I'll see what I can do with this. I'll get a hold of AV again. They claim that we're just all stupid and don't know how to do this. I think what's happening is that Zoom is overwhelmed. Looks like CJ's going to say something.
Yeah, I can actually see those Zoom recordings if you go under the Zoom tab of the Canvas page.
Okay.
So it's working on my end. I don't know about other people.
In my case, I can see under Zoom cloud recordings. I can see the April 1st.
Yeah, I don't think that's where you find it. I think you find it over on the side. I'll see if I can do it, and I'll write detailed notes about how to do it. CJ, if you can do it too, feel free to write detailed notes and send it to either Herbert or me. And we're going to know a whole bunch more about doing things online at the end of this quarter, unfortunately. Anyway, good night all, and I'll see you on Wednesday.